Hello friends, welcome to my YouTube channel. My name is Prathamesh. Without wasting our time, let's begin. And if you please like, share, and subscribe.
Securing enterprise text pipelines requires solving a specific engineering problem, reliably detecting and redacting personally identifiable information from unstructured data, while executing entirely on local hardware, never transmitting that sensitive data over an external network. Sending unredacted enterprise data, proprietary code, or medical records to external cloud APIs creates immediate compliance vulnerabilities and a high probability of data leakage. Relying on cloud-based sanitization pipelines also introduces operational overhead and network latency that slows down high-throughput workflows. To keep execution local, developers have traditionally relied on regular expressions, or regex, deploying rigid pattern-matching scripts to scan text for identifiable structures. But regex relies entirely on enforcing structural rules on natural language. It possesses no semantic understanding of the words it processes. Because it lacks context, pattern matching mathematically guarantees errors. It will flag a string of digits in a complex equation as a phone number, while missing a residential address written in a non-standard format. True reduction safety on local hardware requires moving past simple pattern matching to a system that analyzes deep linguistic context. OpenAI engineered the privacy filter specifically to solve the semantic limitations of traditional scripts. It is an open-source, local-first model built for high-accuracy text sanitization. Instead of searching for structural patterns, the model uses deep language context to analyze how words relate to each other, identifying sensitive data based on its role within a sentence. To understand meaning at scale, the model utilizes a context window capable of processing 128,000 tokens in a single pass. In practical terms, 128,000 tokens allows the model to ingest and analyze the equivalent of entire books or massive code repositories simultaneously. Standard local scripts break text down and analyze it line by line, losing the broader context. Privacy Filter evaluates the document comprehensively. This creates an immediate engineering trade-off. Running a deep context model capable of processing 128,000 tokens on consumer hardware usually results in memory bottlenecks. The central question is how a model can parse this volume of unstructured text locally without exceeding the host machine's memory limits. Answering this requires deconstructing how the model executes bidirectional token classification and how it utilizes a sparse parameter architecture. The model's foundational processing mechanism is bidirectional token classification. This diagram illustrates standard text processing. Basic language models use a unidirectional left-to-right sweep. The computational limitation here is strict. A left-to-right model cannot leverage context from the end of the sentence to understand current terms. A bidirectional architecture layers a simultaneous right-to-left sweep over the sequence, capturing data from both directions at once. Take semantic ambiguity. The word chase could be a bank, a name, or a verb, depending entirely on the surrounding sentence. The model analyzes the statistical state of the surrounding tokens on both sides to calculate the probability of the word's category and resolve the ambiguity. This localized bidirectional resolution process scales across the entire 128,000 token document. Executing this dual-pass system requires significantly more computational overhead than running a lightweight regex script. However, bidirectional context provides a mathematical method for reducing the false positives that occur when using pattern matching tools.
This taxonomy tree maps out the output of that bidirectional processing. Identified sensitive tokens are routed into 8 distinct PII categories. The personal category identifies names and addresses. The contact category isolates emails, phones, and URLs. The financial category targets accounts and credit cards. It also identifies machine-readable embedded technical secrets. Identifying these technical secrets alongside human-readable PII is a requirement for enterprise environments, where development code must be sanitized before being shared. The model masks only the tokens that fall into these 8 categories, leaving the surrounding, non-sensitive textual context readable. This granular mapping provides a high level of operational security, provided the model's inference speed is fast enough for production pipelines. This brings us back to the hardware constraints. Maintaining a 128,000 token context window while executing bidirectional classification requires significant processing power. Standard consumer laptops lack the dedicated video RAM required to load and execute traditional large language models at this scale. The model addresses this through extreme parameter efficiency, utilizing a technique known as sparse activation. Looking at its total scale, the model houses a knowledge base consisting of 1.5 billion total parameters. In older, dense architectures, processing a single data pass would compute across nearly all of these parameters simultaneously, saturating hardware limits. Sparse activation changes this. During inference, the model decouples its total data storage from its active compute requirements. As a specific token passes through the system, the model evaluates its properties and illuminates only a specific, optimized pathway of nodes. Out of the 1.5 billion parameters available, the model uses exactly 50 million active parameters per operation. By utilizing 50 million active parameters, the model reduces its compute footprint, allowing it to run within the VRAM limits of local hardware. Sparse activation is the structural mechanism that makes high-throughput local PII redaction viable for standard enterprise machines. The performance of the bidirectional architecture and sparse activation has been validated through empirical testing. This bar chart compares baseline systems against the model's performance. OpenAI Privacy Filter achieved a 97.43% F1 score. This score was validated against the corrected version of the PII masking 300K benchmark. The F1 score, the harmonic mean that balances precision and recall, is the standard metric for assessing redaction safety. A 97.43% score indicates the system can capture sensitive data while minimizing the risk of the data leaks common in legacy scripts. This accuracy was achieved entirely under the strict constraints of local, off-network execution. These results show that high-fidelity redaction is now possible without a connected cloud server. OpenAI has released the privacy filter as an open-source tool. It is distributed under the Apache 2.0 license, allowing for direct enterprise integration and commercial use. The model is available for download via Hugging Face and GitHub. Furthermore, the architecture is extensible. Engineers can use this foundation and fine-tune it for custom applications. Developers can train the model to recognize niche identifiers specific to medical records or proprietary legal datasets. By combining bidirectional context with an efficient local footprint, OpenAI Privacy Filter provides a new standard for secure, local data sanitization. Every day, data engineers face a strict operational paradox. They need to extract value from massive streams of unstructured data, but they must strictly isolate and scrub sensitive personally identifiable information, or PII. Current cloud-based large language models are highly accurate at redacting this sensitive data. The problem is that transmitting unmasked PII off-site introduces unacceptable latency and serious security risks. The alternative is local edge execution. Historically, however, running data sanitization on local hardware meant relying on systems that lacked the compute power to perform deep semantic redaction. The newly released OpenAI Privacy Filter bridges this exact gap, providing high-throughput execution directly on your own hardware. It is an open-source, local-first architecture that processes up to 128,000 tokens in a single pass, while achieving a 97.43% F1 score for accuracy. To achieve true enterprise-grade data sanitization, pipelines must disconnect high-accuracy semantic processing from cloud dependency entirely. For decades, local data masking has relied on regular expressions, or regex, and rule-based pattern matching. This animated diagram shows the core limitation of regex, rigid syntax. It highlights the numbers, but misses the name Jordan entirely. Real-world documents rarely adhere to standard formatting. When this text jumbles into messy JSON logs, the syntax-based tool flashes red, failing completely. When these edge cases bypass hard-coded rules, the inevitable result is severe data leakage. Human readers, by contrast, easily identify PII in messy text because we read for semantic meaning, not structural patterns. A robust local sanitization pipeline cannot rely on fragile syntax. It has to evaluate data based on deep language context. To replace pattern matching, the OpenAI Privacy Filter utilizes bidirectional token classification. Standard left-to-right parsing often misinterprets ambiguous words, having to wait until the end of a sentence to resolve the context. In this diagram, the bidirectional mechanism evaluates tokens on both sides of a word simultaneously to deduce semantic meaning. This distinguishes Jordan the location from Jordan the person, triggering a validation tag that masks the name.
This contextual depth allows the system to distinguish a harmless internal ID from a sensitive API key or credit card number. The quantitative result of this architecture is a 97.43% F1 score on a corrected version of the rigorous PII masking 300K benchmark. That F1 score represents a near-perfect balance between precision, making sure it doesn't over-redact useful data, and recall, ensuring it catches every potential leak. Bidirectional context solves the accuracy problem of unstructured data masking, but running that level of comprehension locally introduces a massive computational challenge. Achieving deep bidirectional context usually requires heavy, computationally expensive models that cannot run efficiently on a standard laptop. Yet strict enterprise compliance mandates dictate that sensitive financial and personal data cannot be transmitted off-device for processing. The model uses 1.5 billion parameters for high accuracy, but processing them all simultaneously would crush local memory limits. The solution is sparse activation. Most of the network remains inactive, while a streamlined pathway of 50 million nodes illuminates. By routing data exclusively through these necessary pathways, the architecture bypasses inactive parameters to drastically reduce compute requirements. This active versus total parameter ratio transforms the model's footprint, enabling it to run entirely on standard edge hardware. The result is high-throughput data sanitation that easily meets strict local execution mandates. Disconnecting the knowledge base of 1.5 billion parameters from the active compute load of 50 million eliminates the trade-off between privacy and performance. Many local models suffer from small context windows, forcing data engineers to slice long documents into arbitrary chunks. That arbitrary chunking severs the long-range semantic dependencies required by bidirectional token classification. This demonstrates the OpenAI Privacy Filter's capacity, a massive 128,000 token context window, encompassing an entire document. Extensive server logs or sprawling JSON files can be ingested in a single forward pass, applying redactions across the text simultaneously. Preserving the unbroken structure ensures that a specific definition established on page 1 correctly informs a masking decision all the way on page 50. Long context capability operates as a critical requirement for maintaining semantic accuracy in complex enterprise workflows. The model identifies and masks 8 specific categories of sensitive information. These begin with personal identifiers, like names, addresses, and dates, and contact details, including emails, phone numbers, and URLs. It also targets the financial and sensitive category, capturing account numbers, credit cards, and hidden system secrets like passwords and API keys. As shown here, this setup is fully accessible. It is released open source under the permissive Apache 2.0 license and available on platforms like Hugging Face and GitHub. The primary advantage of this open source status is that engineering teams can fine-tune the baseline model on their own custom datasets. Organizations can adapt the deep context engine to target the highly specific niche identifiers required by specialized medical or legal compliance frameworks. This diagram illustrates the complete architectural flow enabled by the OpenAI Privacy Filter. Unstructured data enters local hardware, outputting a completely masked data stream while maintaining a strict air gap from external cloud servers. It completely replaces brittle pattern matching with deep bidirectional context for unstructured text. It captures the accuracy of 1.5 billion parameters using a streamlined 50 million active parameter workflow, and it processes up to 128,000 tokens in a single unchunked document pass. The OpenAI Privacy Filter shifts PII redaction away from a risky cloud dependency, establishing a highly accurate, zero-trust standard for local execution.